Okay, so here we talked about calculating the probability of cat or dog. And so we can kind of generalize this and say the probability of A or B being or being the inclusive or, this can be written as probability of A plus the probability of B minus the probability of A and B. Sometimes we have events that are mutually exclusive, okay? So sometimes events A and B are mutually exclusive, okay? And what this looks like is that whatever we have, there is no overlap between A, this is supposed to be a circle, there's no overlap between A and B, okay? So that basically means the probability of A and B is equal to 0 if A and B are mutually exclusive. Okay, and so the effect that this has is that if A and B are mutually exclusive, then the probability of A or B becomes the probability of A plus the probability of B, and I could include subtracting off the probability of A and B, but that's 0, so I'd be doing a minus 0, so effectively we just get this. Okay, and this is useful because I could ask something like, what's the probability of getting, if we draw a card at random, what's the probability we draw hearts? And you'd say the answer is, if I draw a card at random, what's the probability that I get a heart? Are we familiar with the deck of cards? Okay, there's 13 cards that are hearts. Out of 52, we would say 1 out of 4. Okay, and I could ask, what's the probability of drawing a diamond? Same, 13 out of 52, 1 out of 4. So I could ask, what's the probability of drawing a heart or a diamond? And we know that hearts and diamonds are mutually exclusive. You cannot have a card that is a heart and at the same time be a diamond. Hearts and diamonds are mutually exclusive. Okay, so probability of heart or diamond, this would just be 1/4 plus 1/4, 1/2. So if they're mutually exclusive, you don't have to worry about subtracting any overlap. Otherwise, you do, okay? Okay. In all other cases, you do. So that's for or situations, okay? I may, I'd like to go to the next page. So now we have, I'm going to introduce something called conditional probabilities. All right, and so with a conditional probability, we would say, what is the probability of A given B? Okay, this is read as the probability of A given B, okay? Or we can think of it as the probability that A happens if we know that B has or will certainly happen. Okay, so we could say I don't know. Let's say A is a person speaks English. Okay, so let's say we're going to pick a person at random. Pick a person from the world at random. Okay, and so A will be that the probability that a person speaks English. And actually, I have no idea. We'll say, we'll ask Google. What percentage of the world speaks English?
Here is information from Ethnologue.
That doesn't help me. Ba, 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 ba. I cannot, you are not formatted for mobile viewing. Okay, so English, there are, it says 339 million people who speak English? This sounds low. I don't believe you. All right, English speaking world, let's ask Wikipedia. Okay, I guess 360 to 400 million have English as their native language. Okay, I will accept that. All right. So A is a person speaks English, so we will we'll just ballpark this and say 400 million. We'll say speaks English as native language. Okay, so we'll say 400 million. So the probability that someone speaks English, if there's 400 million English speakers divided by, there's what, 7 billion people? How many people? We'll just say, okay, so if we pick someone at random in the world, we would get about 0.057, okay? So this probability, and if we say 7 billion people, then the probability of A would be 400 million divided by 7,000 million, or 7 billion, and we have 0.057. Okay, this is the probability of A happening. Okay, let's say B is a person is from the United States. Okay. What we have here now is we're going to ask, what is the probability that someone speaks English as their native language if the person we select is from the United States? Okay, so what is the probability that English is native language if we know the person is from the US? Okay? And so what is this value here? Whatever it is, it's much higher than 0.057, okay? Maybe, I don't know, 231 over the population of the United States. So 300, so maybe like 75%. Okay, we're just gonna ballpark it here. This is just an estimate, all right? So what we're saying is that if we know that someone is from the United States, then the probability that this person speaks English as their native language is now 75%, which is much greater than if we just picked someone at random from the world, right? So this is a conditional probability. The probability that A happens changes significantly based on whether or not B has happened. Okay, and so this is what we call a conditional probability. Okay, and so actually the way we calculate A given B, and well actually if you said 231 and we said 300 million, maybe I'm going to change this. I'm going to cheat and say set 0.77, sorry, just so that our calculations will line up. Okay, we're going to say 0.77. Now, how do we get this? Okay, so to calculate the probability of A given B, the probability of A given B is calculated as the probability of A and B divided by the probability of B. Okay, or another way, okay, also we can say if we have the actual counts, we'll say the count of A and B divided by the total count of B. Okay? So we said in the United States, or we'll say, yeah, in the USA, in the US, there are 231 million people who speak English as their native tongue. Okay, and then we'll also say in the US there are, we're just going to say 300 million people. Okay, and so the count of US and English, native English speakers, is 231 million. And the count of US population total is 300 million. So the probability of A given B is going to be 231 million divided by 300 million. And that is 231 divided by 300, 0.77. Is this okay? Did I lose anybody here? Okay, well, no one is saying anything, so I will assume and hope that we're all okay here. Okay. All right. Let me just flip back a couple slides and let me pull out this thing on cats and dogs. All right. Okay, so let me ask, so we have, we've established the probability of cat is 0.25, the probability of owning a dog is 0.3, and the probability of owning a cat and a dog is 0.1, okay? So here's the question. If somebody has, we'll say, what's the probability of having cat if we know someone has a dog? This is basically if we know the person is a dog owner, already owns a dog, what is the probability the person also owns a cat? Okay, and so this is going to be the probability of having a cat and a dog, so 0.1, if we know the person already has a dog, divided by 0.3. So this becomes 0.333. This is different from this. What is this? Point 1 goes in the numerator. Okay, yeah, if the person already owns a cat, what's the probability this person also owns a dog? So we would put 0.1, the probability of cat and dog, in the numerator, and what goes in the denominator? 0.25. Okay, and so what is this probability? It's 0.4. Okay, so we can look at, 10% divided by 25%, basically how many people own a cat and a dog, and we're just limiting ourselves to, basically, in this scenario, we're limiting ourselves just to those people who have cats. Okay, so we're just limiting ourselves to this column, and within this column, what's the probability that you are in the dog box? 40%, and you are 60% chance of being in the no dog box. Okay, or we could look at it this way: if we limit ourselves just to this row with dog versus, just the row where you have a dog, what's the probability that you end up in the cat box? That sounds not there. Okay, 10% out of 30, so there's a 1 in 3 chance here, so 33% there. Okay, and so we can establish this idea of independence, okay, independent events. Okay, so independent events, if A and B are independent, then the outcome of one event has no influence on the outcome of the other event. Okay, so we can think of things that are independent. So, earlier we saw, if A was a native English speaker, and B is from the USA, these are not independent events. Okay? Because if we know someone's from the USA, that changes or affects the probability that someone's a native English speaker. And likewise, if we know someone's a native English speaker, that also affects the probability that this person's from the USA. Okay? But we could say, like, A is coin flip lands heads. And B is die roll lands on 3. Okay? These would be independent. Okay? If the coin flip lands heads or not, it should have no effect on the probability of the die landing on the number 3. Okay, so whether the die lands on the number 3 or not doesn't really care if the coin flip lands heads. So these two things would be independent. All right. So symbolically, if A and B are independent, the probability of A given B should be equal to what? We're asking, what's the probability that A has happened if we know that B has also happened? It's just be the probability of A, exactly. Okay? So if they're independent, the probability of A happening, if we know that B has happened, well, that doesn't help us out. It's just the probability of A. Okay? So knowing that B has happened doesn't really give us any more information, so the probability of A given B is going to be just the probability of A. Okay? So if A and B are independent, then probability of A given not B is also going to be equal to the probability of A. Okay? Which, by the transitive property, means that probability of A given B is also going to equal the probability of A given not B, which is all equal to the probability of A. Okay, so if A and B are independent, then you're going to have these things all be true. If you know that two events are independent, could they be mutually exclusive? Yes, no, maybe. If we know two events are independent, could they also be mutually exclusive? Okay, and the answer to that is if two events are independent, then they for sure cannot be mutually exclusive. Okay, so let's think about that. Okay, mutually exclusive means that if one happens, then the other is impossible, right? Because the overlap, mutually exclusive, means A and B has no overlap. So if A happens, B becomes impossible. So that means the outcome of A does affect B. Does influence the probability of B. Okay, which means A and B are not independent. Because independent means the outcome of A has no influence on the outcome of B, or that the outcome of B has no influence on the outcome of A. Yes, question. If they have no overlap? So mutually exclusive means there's no overlap, right? Okay, so mutually exclusive means that there's no overlap, meaning that if A happens, then B is no longer possible. Okay, so it'd be like the card I draw is a heart versus the card I draw is spades. Okay, if I draw a card and I know that it's a heart, I know automatically that it can no longer be a spade. Okay, or if or mutually exclusive could be that the card is red versus the card is spades. And so let's say, I don't know, you're playing poker and you need a spade to complete your flush or something, okay? But then as soon as they start turning the card over, you recognize that it's red, okay? So without even needing to know what the card is exactly, as soon as you see that it's red, you know that you didn't get the spade. Okay, so mutually exclusive means there's no overlap, so as soon as A happens, B becomes impossible, okay? Independent means that whether A has happened or not doesn't influence the probability of the other thing. So being an ace is independent of whether the card is a heart or not, okay? So even if I tell you, so if we draw a card at random, the probability that that card is an ace is 1 out of 13, okay? Because there's four cards in the deck that are aces, okay? Now if somebody says, well, I just drew a heart, okay? What's the probability that the card is an ace? It's still 1 out of 13. So drawing an ace is independent of whether or not the card is a heart. So knowing that the card is a heart doesn't change the probability that the card is an ace. Okay, so let's just try a silly example here. Okay, based on some I don't know, silly but I'm thinking non-offensive stereotypes. Okay, so we'll say, is there are the events someone is from Texas independent of whether that person owns a truck? Okay, so we can say, let's just let's say we'll just have two groups of people. We'll say we have people from California and people from Texas. Okay, so we'll build a table here. Okay. Okay, so we'll say what's the population of California? We'll say 37 million. What's the population of Texas? Population of Texas.
The population of Texas was 26.96 million in 2014.
27 million, okay. All right, and then we'll say owns a truck and no truck. And I don't know what these numbers are. I don't think Lady Google knows either. Okay, so 37 plus 27, that's what, 64 million people? Okay, so I'm just going to completely make up numbers. Don't get mad at me. So we'll say in California, I don't know, 9 million own a truck and 28 million do not. And in Texas, we'll say 13 million own a truck and 14 million do not. Okay, and so we'll say a total of 22 million own trucks and what is this? 42? Did I add that correctly? Okay. Just making stuff up here. Okay, so then we want to know, is truck ownership independent of what state someone is from? Okay, so how can we check this? So we want to know, is Texas independent of truck ownership? Okay, so if they were independent, what would be true? Okay, so if A and B are independent, what is true? Yeah, if A and B are independent, then probability of A given B will equal the probability of A, right? So let's just try this out. If Texas and truck are independent, then the probability of Texas given truck should equal the probability of being from Texas. Are we in agreement here? Okay. So what is the probability of Texas given truck? Okay, we would say this is the probability of Texas and truck. And in the denominator we would put what? Probability of truck, right? Or if not probabilities, then we can just deal straight with counts. And so this would be 13 over 22. So this number over here is 13 over 22.591. Okay? So if in our group, if you own a truck, there's now a 59% chance that you are from Texas. Okay. All right. If overall, what's the probability that someone is from Texas? (27 out of 64), right? So if we select someone at random, probability that this person is just from Texas is 27 out of 64, 42% chance. (422). Oops. Okay. And so we would say, okay, the probability that someone picked at random is from Texas is only 42%. Okay. As soon as we know someone owns a truck, then the probability that this person's from Texas jumps up to about 59%. Okay? And so because these things are not equal, so probability of Texas given truck does not equal probability of Texas, this tells us that being from Texas is not independent of truck ownership. All right. Does that make sense? Okay. Okay, and so for now, we're just going to say if they are not exactly equal, then that means they are not independent. And that might, so we'll just say for now, if, probability of A given B does not equal probability of A, okay, then we will say they are not independent. Okay, but later on, we will decide whether or not the difference is significant, okay? So, here's an example where we might ask, what is there a difference between, I don't know, the percentage of is, I'm trying to, is wearing jeans independent of, we'll say, California versus Texas, okay? And then, and perhaps, and just for simplicity, let's say probability of jeans given California, let's say is like, I don't know, 85%. And we'll say probability of jeans given Texas is 86% or something like that, okay? So they're very close. So for now, we would just say, because these two things aren't exactly equal, we would say they are not independent, okay? But later on, we will come to decide whether or not the difference between 85% and 86%, is this difference significant, okay? So later, we will test to see if the difference between 0.85 and 0.86 is significant, okay? And this is going to be called the two proportion test. So for now, we're just going to say, oh, they're not the same, they're not independent, okay? But later on, we might be like, oh, 85, 86%, that's not very different. Maybe they are close enough to say that they're independent, okay? Or maybe 85 to 86% is different enough for us to say that they are independent. Oh, I'm gonna run out of time here. Okay, I think I'm gonna have to leave it to you and your reading on to learn about sequences of independent events. So let me just say the important thing is that you might have, if A and B are independent, then the probability of A and B suddenly becomes probability of A times the probability of B, okay? So it's like probability of getting heads, then heads. So this would be probability of heads and heads becomes a probability of heads on the first. So heads on the first and heads on the second becomes heads on first times the probability of heads on second. So this becomes 1/2 times 1/2. So the probability of getting heads and heads is going to be 1 out of 4. Okay. You'll have there are a few exercises in the homework that cover this, and I'll have to leave it to you there. Okay. So we'll end there, and we'll see you guys. Have a good Independence Day, and we'll see you guys next Wednesday.